practice with the geometric. So if I asked you then, for example, to find the sum of the following. I'm going to put a dot, dot, dot there, so there's some terms in the middle. Okay. So let's first just write out what we're dealing with here. So I'm finding the sum. This is good practice for summation notation of the series. And what's the explicit formula for the series? Good. 4 times negative 1/3. We're putting that in parentheses to the n minus 1 power, or we can use k minus 1. If we use an n, we just put an n here instead of a k. So then this would be considered the first term. Be careful here. Even though there's a 10 here, what value of n produces a 10? 11. So that's really the 11th term. Okay? So to do that, we're going to use the formula a sub 1 times 1 minus r to the nth over 1 minus r. And we're going to make sure we're careful about using parentheses around r. Okay? So what's a sub 1? So we're going to do 1 minus a negative 1/3 to the 11th over 1 minus a negative 1/3. Okay, so down here we could do minus a negative 1/3 and make it 1 plus 1/3, right? But order of operations up here, this is why this parentheses is important. This wouldn't be an addition sign, because what would we have to do first? Negative 1/3 to the 11th. Okay, so that's why it's important to have that there. So when you're inputting this in your calculator, you can put it all in if you want. Just make sure you're real careful with parentheses. So I'm going to just do this. By the way, if a 4 is in front, that's the same thing as being on top. I'm going to first do the numerator, and then I'm going to divide it by the denominator. So that's the top. And then on the bottom, divided by 1 minus a negative 1/3 or plus 1/3. And we get that it's approximately. Interesting, okay. Now, it isn't exactly 3, because there's that 16935 after that, so I'm just going to put those dots there to indicate that it's not exactly 3. Just a quick question, what do you think would happen if I added like on the 12th term and so on? I'm going to just check it out a second, because this leads exactly into what I was talking about next. Let's say I took this and I said, hey, through the 11th term it's 3, right? Let's try to find it through, how about the 20th term, and see what happens. Okay. Did it change a whole lot? No, it didn't. Even though we added like 9 more terms on, okay? So if we would keep adding on terms, these terms as we keep getting bigger, because we're multiplying by 1/3, right, are going to continue to get really, really, really tiny. So what that leads into then is something called an infinite series, and we wouldn't say that we could find the sum exactly, but we could get so close that we can say it's the sum, but only for certain ones. So this is finite. Finite means it stops, okay? What's infinite mean then? So an infinite series means that if you were seeing it in summation notation, here would be a key. They would start at 1 and then it would go to infinity at top, on the top. So that's one way. And if you were actually seeing the terms, another way would be that you'd have terms, but then at the end you wouldn't have a last term. You would see those 3 dots just to show that it continued. Okay, so earlier on, a couple days ago, gosh, it was probably Friday now, do you remember how we talked about those words converge and diverge? Do you remember how some of the series, or some of the sequences, converged because they got closer to one value? Okay, so this is what it has, that's what it has to do with. If we're looking at a sum of things where the sequence is converging, we can actually find their limit, okay? And then if we're looking at one where it doesn't converge, then we can't. So we can only find the sum of a series if it converges. So let's take a look at one, and you can decide if it does or not. Let's take 0.1 plus 0.01 plus 0.001 plus 0.00. Okay. And I'm going to use something called partial sums here. Partial sums means I can't find all of the whole sum, agreed? But I could find the sum of the first 2 things. Okay, let's find the partial sum of the first 2 things. Just add the first 2 things together. What do you get? Yeah, 0.1 plus 0.01. 1. Okay. How about the third partial sum? The third partial sum is, what if I just added the first 3 things together? 0.1 plus 0.01 plus 0.001, what would you get? Okay, now let's do the fourth partial sum. What's the fourth partial sum? Okay, are you seeing a pattern here? Okay, what do you think the fifth partial sum would be? Yeah, 0.11111. Okay, so does it look like these sums are approaching a value? We're doing sums now. If you had to guess, what are these sums approaching? Really?
Point 2.
Guys. You don't know what this is called? 0.1 repeating. Okay, if this was going to continue forever, wouldn't the sum approach 0.1 repeating? Okay, so.
Wait. I thought that was 0.1.
It isn't. This is 0.11. This is 0.111. This is 0.111. If I added these all up to infinity, what would the sum be? It would be 0.1 repeating. By the way, what fraction is that? Well, let's find out. Take a look at your infinite series. By the way, the infinite series, if you notice there, it says where the absolute value of r is less than 1. You can only infinite series converge if what you're multiplying by is less than 1. It could be positive or negative. That's why the absolute value is there. Okay, you guys tell me, what's the first term? 0.1. What are you multiplying by? Okay, so would you agree that 0.1 is the same thing as 1/10? And what are we multiplying by? By 1/10. Okay, so let's plug this into, do you see there's a different formula for an infinite series? And that formula is, we're going to find out what this converges to, what the fraction is, since some of you don't know. It says you do a sub 1 on top, which is 1/10, over 1 minus r on the bottom. All right, let's do our fraction skills. What's 1 minus 1/10 as a fraction? 9/10. Thank you. We have 1/10 divided by 9/10. If you multiplied by the reciprocal, what fraction would that give you? 1/9. So, 0.1 repeating is the same as 1/9. Okay. So this would be an example of an infinite series where we could find the sums. So even though it goes to infinity, we are still able to find the sum of that. For some of them, they're going to be just so close to that number, we call it a limit, okay? But we're going to be able to find their sums. And again, the only time that we're going to be able to do that is if r is less than 1. All right, so let's do one more. By the way, notice there's a word in front of a word after the infinite. What's the word after the infinite on your formula sheet? Right after it. Geometric. The only sums that converge are geometric ones, not arithmetic. An arithmetic one will never converge because arithmetics are adding or subtracting, so they're always going to be approaching like an infinity or a negative infinity. But how about something like this? Okay, so let's write the explicit formula for this. And then we can even play around with the partial sums if you want, okay? Wouldn't you agree that the explicit formula for this would be 1 times negative 1 to the n minus 1 power? Okay. So I'm going to point out to you, this is r. On the previous page I said the only time that these converge is if the absolute value of r is less than 1. Is that true? Is that true? No. It's not less than 1, it's equal to 1. So if it's exactly equal to 1, let's see if it converges or not. I'm going to do some partial sums. Partial sums just means add up part of the sequence. So the first partial sum would be 1. The first term is just 1. The second partial sum, add the first two terms. What do you get? 0. The third partial sum, 1. The fourth, okay, what's going to continue to happen? 1, 0, 1, 0, 1. It's going to keep alternating. It's not going to approach one single number or get smaller like the one before. And so when that happens, this does not converge. And if it doesn't converge, we cannot find the infinite sum. So please don't run around trying to use this formula on everything. It's only a small portion of things that we can use it on, okay? And that's if r converges. So that's an interesting question then. You know how that last one was a 0.1 and 0.11 and think about any repeating fraction. Couldn't we write any repeating fraction then as a series? Like for instance, give me a repeating decimal. Do one with 2 digits. With 2 different digits. 0.1818181818. Okay? The first term would be this. The second term would be 0.0018, right? Well, the next one would be 0.000018. What would the next one be? If I would start adding these, like the second partial sum would be 0.1818. The third would be 0.181818. The fourth would be, and so on. What's the first term? Write it as a fraction. Write it as a fraction. What's 0.18 as a fraction? 18 over what? 100. And what am I multiplying by? 1/10 would move the decimal over one spot. 1/100. If you plugged that into the geometric series, watch what would happen. (18 over 100 divided by 1 minus 100. We're trying to write this as a fraction now. We're trying to figure out what fraction this is. So you guys tell me what's 1 minus 100? 99/100. So on the top I have 18 over 100 divided by 99 over 100. $18.99. Type that in your calculator and tell me what you notice. Ha! Crazy.